Okay, gents, this is going to be my first attempt at doing a lecture via an iPad using Explain Everything. Now, I'm going to introduce the topic geometrical applications of the derivative, and in particular talk about what an increasing and decreasing functions are and what it means to be stationary, a function to have a stationary point or several of. So, this all has to do with the derivative, and in particular, when you derive a function, you actually find the gradient of the tangent at any given point. Now, if the gradient of that tangent is positive, then you have, whatever values that it is positive, the function is said to be increasing at that point there, although or several points. If the gradient of the tangent at any part of the function is negative, well, at that part, it is said to be a decreasing function. So we've spoken about when the derivative is positive or negative, but then there is the case when the gradient is in fact equal to 0. So it's neither positive or negative, and when the gradient is equal to 0, you have a stationary point. Okay, what that means is, if you look down at the diagram here, which I'm about to highlight, oh, let me change that, put it in red so you can see. So we're going to focus in on this diagram here. If you look at that, I want you to focus in particular on the points B, F, and H. They are stationary points, because if you draw the tangent there, you get a horizontal line, which, as you guys should know by now, has a gradient of 0. So B, F, and H are stationary points. Now, which of these points would give you an increasing function at that point? What that means is the gradient of the tangent is positive. Well, if you look at A and G and you draw tangents at those points, they would clearly be positive. Therefore, at A and G, this function is increasing. If you then go ahead and look at C, D, E, and I, you can see when you draw your tangents, you'll have a negative gradient. Okay, so when we introduced this topic, we first started about talking about increasing, decreasing, and stationary points. You need to be able to break down a function and clearly state where it is increasing, where it is decreasing, and where you have stationary points. And hopefully I've defined how, in this case, in this diagram here, B, F, and H are stationary. It is increasing at A and G because it has positive gradient of the tangent there, and it's decreasing at C, D, E, and I. Okay, next page. Oh. So, let me just expand this, make it a little bit small for you to see. Not good there. Alright, let's leave it as that for the time being. So I just change colour. Okay, so this is a worked example here. It says differentiate the function x cubed minus 12x, hence find whether the curve y equals f of x is increasing, decreasing, or stationary at the point. So if you look at A there, it wants to know whether this function is increasing, decreasing, or stationary at the point x is equal to 5. What that is asking is when you find the gradient of the tangent, is it positive, negative, or equal to 0? So let's derive this function here. So f dash x will be equal to 3x squared minus 12. Now let's look at the point where x is equal to 5. So when it's equal to 5, you end up getting 3 times 5 squared minus 12. So you get 75 minus 12, which is equal to 63, which, as you can clearly see, is greater than 0. Therefore, at x equals 5, this function, so this function is increasing. Okay? You do the exact same process for x is equal to 2 and x is equal to 0. I'll just do one more, I won't do all of them. So let me just draw that page there in half so we can focus on when x is equal to 0 and see what happens in that case there. So, I'll do a different colour. So when x is equal to 0, the process is the same. This question is asking us for when this function is increasing, decreasing, or stationary. So you derive it because you want to find the gradient of the tangent, then you substitute the point, and we've already derived it there, so we don't need to do that again. We just sub 0 in straight up. So when you sub in 0, you end up with 3 times 0 squared minus 12. Well, 0 squared is 0, times it by 3 is 0, so you're just left with minus 12. Therefore, which you can see is less than 0. So therefore, at x equals 0, this function is decreasing. Okay, you could have also tried x is equal to 2, and if you substituted that in, you actually would get a stationary point, because at x is equal to 2, the first derivative is equal to 0, which means the gradient is equal to 0 there. Okay, let's go to the next. Alright, another worked example, and then I feel that you'll be ready to take on some homework now. So, states show that f of x is equal to x cubed plus x minus 1 is always increasing. Well, what that means is the gradient of the tangent is always positive. So if we derive that, because that's how we find the gradient of the tangent, you get 3x squared plus 1. Yep, 3x squared plus 1. So, how could you show that this is increasing? Well, you'd have to show for no matter what value of x, you would get a positive number. The reason being is since x squared, no matter what x is, negative or positive, when you square a number, it will equal a positive, then you're always adding 1. It is impossible for what any value of x you substitute in to get a negative answer, or 0. Therefore, you could explain that in words. So you'd show that 3x squared plus 1 is greater than 0 as x squared is greater than 0. So you've explained that it's always greater than 0 as x squared is greater than 0, and there's that. Then states find f of 0. Well, I just wanted to do this question to show you the notation. What that means is you sub 0 into the original function, because it's not f dash x, it's just f. So f of 0 would equal 0 cubed plus 0 minus 1, so it equals minus 1. Alright, you do f of 1, and you can do this, so I'll just quickly solve this. 1 plus 1 is 2 minus 1 equals 1. Alright, hence explain why the curve has exactly 1 intercept. Well, I'm going to verbally explain that because I've ran out of room. But you'd describe the fact that the function is always increasing, so the gradient is always positive. So once it cuts the x-axis, it'll never go back down, because for it to cut back down through the x-axis, the function will have to be decreasing. But in part A, you've proven that it's always increasing. I hope this helps. And your homework will be to watch this lecture, have any questions prepared for myself when you get to class next, and then we'll do some work.